The p block elements, group 15. Nitrogen, phosphorus, arsenic, antimony, and bismuth are the elements. Nitrogen and phosphorus are nonmetals, arsenic and antimony metalloids, and bismuth is a typical metal. Nitrogen 78% by volume of the atmosphere, and it occurs as sodium nitrate NaNO3 called chili saltpeter, potassium nitrate Indian saltpeter. It is found in the form of proteins in plants and animals. Apatite Ca3PO4 taken twice, CaF2 type, or Ca9PO4 taken 6, CaF2. That means 3 moles of calcium phosphate, 1 mole of calcium fluoride. For example, fluorapatite formula Ca9PO4 taken 6, CaF2. Sometimes it is given 3 Ca3PO4 taken twice, CaF2. And coming to the phosphorus, it is present in bones as well as living cells. Phosphoproteins are present in milk and eggs. Arsenic and antimony bismuth are found mainly as sulfide minerals. Here, interesting things you see. Delta H ionization of bismuth is bit more than stibbium, antimony. Ionization enthalpy 1, 2, 3, 3 are given. 1 is common, there is no change. But second ionization potential, third ionization potential, slightly you can see some differences. Electronegativity, these two are having same 3.0, 2.1, 2.0, 1.9, 1.9. Phosphorus electronegativity, hydrogen electronegativity same. You can notice that. Melting point, you see 63, 317, 1089, 904, 544. And some things are nonsense to mention here. These three are anions and these two are cations. Of course, cations are small in size. So there is no need to worry about such kind of trends. But this is up to arsenic it is increasing, then slightly decreasing. See, these are mentioned here, cations and anions type. Electronic configuration NH2NP3, fine. Atomic radius from arsenic to bismuth, only a small increase in covalent radius is observed. Generally increases, but that is very small. Ionization enthalpy, just now we were discussing. Electronegativity amongst the heavier elements, the difference is not that much pronounced. General down the group decreases, but not that much pronounced. 3, 2.1, like that we are doing. Dinitrogen is a diatomic gas while all others are solids. Except nitrogen, all the elements show allotropy. Whatever the middle lines are there, these are not important. That's why I'm not reading them. Oxidation states -3, +3, and +5. In that -3 oxidation state decreases down the group. +5 oxidation state also decreases down the group. The only well characterized bismuth compound is bismuth 5 compound is bismuth +5 compound is BiF5. Down the group +3 stability increases due to inert pair effect. Nitrogen exhibits +1, +2, +4. Actually, nitrogen exhibits -3, -2, -1, -1/3, 0, +1, +2, +3, +4, +5. All states are possible for nitrogen, wide variety of oxidation states. Phosphorus can also exhibit, but not up to that, up to the mark you can say, not like exact nitrogen. In the case of nitrogen, all oxidation states from +1 to +4 tend to disproportionate in acid solution. Tend to disproportionate in acid solution means they go increase as well as decrease. That means they can undergo reduction as well as oxidation. For example, HNO2, you see here the oxidation state is +3, so it goes to +5 as well as +2. So this is very, very important line. In case of phosphorus, all intermediate oxidation states disproportionate to +5 and -3 in both alkali and acid medium. This is acid solution, you remember, these kind of things are only mentioning in NCERT. However, +3 oxidation state in case of arsenic, antimony, and bismuth becomes increasingly stable due to with respect to disproportionation, and that you can mention because of inert pair effect type. Nitrogen maximum covalence is 4, remaining all can show up to 6, example PF6 minus. Nitrogen differs because of small size, high electronegativity, high ionization enthalpy, and non-availability of d orbitals. P pi P pi multiple bonds with itself and others, nitrogen can form. For example, carbon and oxygen it can form. Heavier elements do this group. Heavier elements of this group do not form p pi bonds, as their atomic orbitals are so large and diffuse that they cannot have effective overlapping. Nitrogen triple bond energy is 941.4 kilojoules per mole, very high. And one interesting line is here. You see, phosphorus, arsenic, antimony, they form single bonds. This is interesting. You see, single nitrogen bond is weaker than single pp bond. This you don't accept generally, our mind won't accept, but this is true. The reason is very simple: electronic repulsions in nitrogen because of small size. Catenation tendency is weaker in case of nitrogen than phosphorus, you can say. Another factor which affects the chemistry of nitrogen is the absence of d orbitals. Because of that, it cannot form d pi p pi bonds, whereas remaining can form d pi p pi bonds, as the heavy elements can. Phosphorus and arsenic can form d pi bonds also, but very rarely, and these are the examples. Reactivity towards hydrogen means hydrates. They are going to form EH3 type of hydrates. Okay, like NH3, PH3, ASH3, SbH3, BH3, ammonia, phosphine, arsine, stibine, bismuthine. Stability of hydrates decreases from NH3 to BH3. Reducing character of the hydrates increases. Ammonia is only a mild reducing agent, while BH3 is the strongest reducing agent. Basicity, ammonia is best, BH3 is worst. See, ammonia melting point is almost high because of hydrogen bonding. Boiling point is, it should be here because of hydrogen bonding. Bond angle ammonia 107 because of sp3 hybridization, remaining pure orbitals. So approximately 93.6, 91.8, 91, close to 90 degrees. Towards oxygen reactivity, all these elements form two types of oxides, E2O3 and E2O5. In that, oxide in the higher oxidation state is more acidic than that of lower oxidation state. Acidic character decreases down the group, because down the group we are going with metals. Metal oxides are basic. E2O3 of nitrogen and phosphorus are purely acidic. That means N2O3, P2O3 are acidic. Arsenic and antimony are amphoteric, and those of bismuth are predominantly basic in trioxides. Reactivity towards halogens. Nitrogen does not form pentahalates due to non-availability of the d orbitals. Pentahalates are more covalent than trihalates. Fuzzen's rules. Trihalates of these elements, except those of nitrogen, are stable. Only NF3 is known to be stable. Trihalates except BiF3 are going to be covalent in nature. Reactivity towards metals. All these elements, they are going to show -3 oxidation state, like calcium nitride, calcium phosphide, sodium arsenide, zinc antimonide, magnesium bismuthite. Very simple, nothing special in that. PH3 has a lower boiling point than ammonia because it lacks hydrogen bonding, where ammonia has hydrogen bonding. Dinitrogen, it can be prepared by treating NH4Cl with NaNO2. And one more reaction will be there, that is NH4NO2. Ammonium nitrate on heating also gives nitrogen gas. Ammonium dichromate on heating gives nitrogen gas. Very pure nitrogen, barium azide gives you sodium azide or barium azide. This was once asked, but nowadays it is not in the syllabus. Nitrogen is not there in the syllabus, don't worry. Dinitrogen is a colorless, odorless, tasteless. When it is not in the syllabus, why I am reading? 2-3 important points are there. For that purpose we are discussing, right? Nitrogen is a colorless, odorless, tasteless, and non-toxic gas. Nitrogen 14-15. It is inert at room temperature because of high bond enthalpy, but it can join with all this, and one ammonia reaction will be there. This is our very familiar reaction. This happens at about 2000 Kelvin, very high temperatures. Generally, when thundering and happening, then you can expect that reaction. Ammonia not required, so this we are taking out. Phosphorus, okay. Oxides of nitrogen, this you can expect. Very interesting. Dinitrogen oxide N2O plus 1 oxidation state can be prepared by heating NH4NO3, colorless gas and neutral, diamagnetic. Nitrogen monoxide, nitric oxide you can say, NO, Dinitrogen oxide is nitrous oxide, laughing gas. Nitrogen monoxide is NO. Plus 2 oxidation state can be prepared by treating NaNO2, FeSO4 and H2SO4. Or you can say N2 plus O2 gives rise to 2NO, no problem. But the temperature is 2000 Kelvin. It's a colorless gas, neutral and paramagnetic. Paramagnetic. This is not mentioned here, paramagnetic. Dinitrogen trioxide, nitrogen sesquioxide, N2O3, oxidation state is plus 3 NO and NO2 or N2O4. You will be getting the blue colored solid, acidic, diamagnetic. And when you drop this in water, you will be getting there HNO2, that's why it is acidic. Nitrogen dioxide, NO2 plus 4 oxidation state. On heating lead nitrate, you will be getting there NO2. Brown color gas, acidic. When it undergoes dimerization, it becomes N2O4, dinitrogen tetroxide, which is diamagnetic. NO2 paramagnetic, N2O4 is diamagnetic. It is a colorless solid and acidic in nature. Dinitrogen pentoxide, N2O5, HNO3 on dehydration you will be getting there N2O5 using P4O10. It is diamagnetic. And when you dissolve this in water, you will be getting the HNO3. NO2 is called a mixed anhydride because on dissolving it gives HNO2 and HNO3. Mixed anhydride. Then structures. Okay, now it's a linear one. About this, they will be asking you the formal charges. What is the formal charge of first nitrogen? 0. This middle nitrogen, it is going to be plus 1. This oxygen, when oxygen is double bond, and this, okay, now here 2 lone pairs are there, no, sorry. When nitrogen, triple bond nitrogen, single bond oxygen is given, this is 0, this is plus 1, this is minus 1. When nitrogen, double bond oxygen is given, this is 0, this is plus 1 and this is minus 1 because 2 lone pairs are there. So minus 1, 0, sorry, minus 1, getting confused again. 1 second, let me clear this. Yes, I will write now. This is minus 1, this is plus 1, this is 0. This is 0, this is plus 1, this is minus 1. Clear? Yes. And NO, this is containing odd electron. You can say this is a molecule with odd electron bond. Okay, now that can be shown like this. N, like this also, 3 electron bond. This can also be mentioned sometimes, you can check. Remaining all are expected things. N2O3 and all. Why does NO2 dimerize? NO2 contains odd number of valence electrons. It behaves as a typical odd molecule, so undergoes dimerization. Nitric acid is not there in the syllabus. Don't worry. Don't worry. Phosphorus allotropic forms are there, right? White phosphorus is a translucent white waxy solid. It is poisonous, insoluble in water, but soluble in carbon disulfide and glows in dark. That is called chemiluminescence. This reaction is very popular to you. You know about this very well. Disproportionation reaction. You are balancing this in redox reactions lesson. White phosphorus is less stable. Angles are only 60 degrees in this. Because of that, it is very unreactive. It readily catches in fire and gives dense fumes of P4O10. It consists of discrete tetrahedral molecules as shown in this figure. Red phosphorus is obtained by heating white phosphorus at 573 Kelvin. White phosphorus 573 Kelvin, red phosphorus 473 Kelvin, beta black phosphorus. Red phosphorus, when you are heating up to 803 or 873, you will be getting there alpha black phosphorus. You need to remember these temperatures. It's odorless, non-poisonous, insoluble in water as well as in carbon disulfide. It does not glow in the dark. And it is polymeric, consisting of chains of P4. Now you see there is no bonding here. This bonding is not there. This bonding is not there. Instead of that, you are having this bond and it is going to be a polymer. Then black phosphorus, as I told you, 2 types. Alpha black phosphorus is heating by the red phosphorus 803 Kelvin, and beta black phosphorus is prepared by heating 473 Kelvin white phosphorus. So phosphine is not there in the syllabus, don't worry. Phosphorus trichloride, phosphorus pentachloride also not required. Okay, don't worry. Just remember this pyramidal shape, sp3 hybridization. We know all this from our regular topic. And these kind of things are important. PCl4 plus and PCl6 minus, we discuss all these points in chemical bonding. PCl4 plus is tetrahedral, PCl6 minus is octahedral, solid state. Oxoacids of phosphorus, this was actually interesting, but it is not there now. Group 16 starting. Yes, so that's all.